Welcome to Phantastic Physics. Today we're going to learn about the design and analysis of a structural member called a column. So what is a column? A column is a vertical load-bearing member, and that means there's forces that are going to be, let's say, on this beam of this building, and the beam is sitting on two columns in this example, and let's say those columns are sitting on foundations that are underneath the earth. So here's my setup. So the column is this member here that I'm going to shade in. And so this beam is going to be supporting forces on the floor above. I'm going to label all of those as F for force. And they could be people, equipment, or other materials that are pushing down on this beam. That beam is going to transmit this force through the column. And the column's job is to take that force and push it down into the foundation. So this would be called a footing. That's a shallow foundation for a building. There could be deep foundations like piles, but basically the column is the intermittent load-bearing member between the beam above and the foundation. So its job is to transmit that force into the earth. So a column, if you think about it, always has, or usually has, force pushing down on it, and the footing or the foundation is going to react by pushing back up with an equal and opposite force. So columns are typically designed to be in compression. So columns are going to be squeezed together, and there's actually two ways that a column can fail. So the primary methods of failure for a column, let's erase this. The first mode of failure is what we call buckling failure. So if you have a really long, slender column and it's feeling a force pushing down on it and another force pushing back up, so it's being compressed, what that long, slender member is going to do, and I'm going to draw this in dashed lines here, is it's going to buckle. So it'll start to bend at some point if it feels too much force. It buckles out in this direction, and if it buckles too far, it's going to suddenly and catastrophically collapse. The other mode of column failure is called crushing. So if you have a shorter and stouter column that's more wide, it's not likely to buckle because it's just not slender enough to do that. So it's going to maintain its rigidity and its shape. But if this thing's made out of concrete, so if this is a concrete column, at some point this force is going to exceed the concrete's ability to withstand it, and all of a sudden it will just basically shatter and buckle, and we call that crushing. So the concrete is going to crush, and basically all the concrete bits fly away, and you're left with just the rebar inside of the concrete column, which is not enough to support the building anymore. So that's going to be a sudden and catastrophic failure as well. But today we're going to be focusing on this mode of failure, buckling, because it's more common than this mode here. Okay, so most buildings have longer, more slender members, and nowadays we build a lot of columns out of steel. So they're more likely to buckle than they are to crush. So as engineers, we do not want columns to buckle. So we have to figure out how to prevent that from happening. Well, what are the factors that affect a column's resistance to buckling? So what are things we could change about a column to give it more resistance to that buckling? Well, the first is material. So the first factor is, what material is your column made out of? If it's made of steel, it's going to have a lot of strength. Steel is very, very strong in compression and in tension, so it's a really good material. If it's made out of concrete, well, concrete is pretty good in compression, not quite as strong as steel in compression, but still very good. The weakness of concrete is it's very poor in tension, so we have to add rebar to help with tension, but we don't really have to worry about that because a column is typically a compression member. The length of the column also matters, right? So if I have a really long column, that's actually going to be more likely to buckle than the short column. So we have to really watch out for length, especially if we're talking about buildings with very tall floor prints. Because if each floor of your building is like 20 feet tall, and this building only has 12-foot tall floors, the one that's 20 feet tall is more likely to buckle than the 12-foot tall column, okay? The other factor is cross-sectional area. So if I were to like take this column and rotate it and just look straight in on the long dimension, would that look like a square column? So if I were to draw it in 3D, something like this, would it look like a rectangular column like this? Would it be a circular column? A lot of times we use what's called an I section. So something like this. I'm sure you've heard of I-beams. So these are very common for beam members, which would be the horizontal members, but they're also very common for columns as well. So an I section, and you could have all sorts of things. You could have a solid circle, you could have a hollow circle. So the actual shape matters quite a bit, right? That's going to determine its rigidity, its resistance to bending. The shape, right? So I talked about shape, but also the cross-sectional area, like how much area is this shape? Is it a small diameter? Is it a big diameter? Is it a small rectangle? Is it a large rectangle? So it's not just the shape, but it's how much cross-sectional area it is, right? How thick that column is. And how the ends are secured. So we're going to spend some time talking about this, but basically the top of the column and the bottom of the column are going to be secured to the support above and below. And there's different methods of securing that column. And based on how rigid these secure points are, that's going to determine how much resistance this column has to buckling. So now that we know what factors affect the column's resistance to buckling, we actually can derive this equation, and I won't go through the derivation, but this is the final form of the equation that calculates what's called the Euler critical buckling load. It has a weird name. Euler is spelled E-U-L-E-R, critical buckling load. And so this equation is named after a scientist who did a lot of work in various fields, but Euler critical buckling load. So this is the load, and P stands for load. So think of that as a force. So instead of having forces pushing on your column, you could just replace the F with the letter P. So P critical stands for the critical force, the critical load that will cause a column to buckle. So this is the maximum force that this column could withstand before it buckles. And so that force for any column can be calculated by taking pi squared. So pi is just 3.1415, you know pi. Pi squared times this capital E, which stands for, so E is called the modulus of elasticity. And I'll explain what that is in just a moment. So E is a measure of the stiffness of the column that comes from the material that it's made out of, times I, and I stands for moment of inertia, which is another measure of the column stiffness, but this one's related to the cross-sectional shape and how that shape is arranged. So we'll get to that in a moment as well. And that is all divided by KL squared. So K is basically an indicator of how the column is connected on both ends, right? So is it, and we'll talk about the different connection ways, so I'm not going to get too into that just now. And this L stands for length. So that's the length of the column. So that is how long is this column from top to bottom, okay? So pi squared times E times I over KL squared. And I think the first thing I need to do is explain what is E, what is I, and what is K. So that's what I'm going to do next. All right, so we're going to start with E, the modulus of elasticity. So what does that represent? E is a measure of stiffness, or how resistant is this column to bending. And the modulus of elasticity actually comes from the material itself. So steel has a very high modulus of elasticity, a very high stiffness. And we get this number by conducting what's called a tensile test in the lab. So if we take a segment of this steel and we pull on it with tension, this E value that basically tells us how resistant is it to that tensile force. So we do a laboratory test and we get this E value from that data, okay? So steel would have an E value, and there's different grades of steel. Very stiff steel would have a very big E, and aluminum would have a lower E because it's less stiff. Aluminum would stretch a lot more than steel would. And so every material has an E value, a modulus of elasticity. And again, that's just a stiffness value that's associated with what kind of material it is, right? And you can see E is on the top of this fraction. So mathematically, that means the greater the E value, or the greater the modulus of elasticity, the higher the critical buckling load this column can withstand. Or in other words, the greater the E, the more force this column can take before it buckles. And that's a good thing. So we want a very big E value. Okay, so now we're going to talk about I, which remember in our equation is called the moment of inertia. So what exactly is that? Well, imagine this column was an I section, and that's no coincidence. There's a reason why we like to build sections in this I shape, and I'm going to show you why, right? So I sections are used commonly for columns, especially steel columns, because what they're really good at is if you imagine this central axis right in the center, this column could rotate around that axis, right? So it could buckle around this axis. And so I tells us it's a measure of how I'm pushing area away from this axis of rotation. So in other words, like I could have a shape that's just a circle like this, but the disadvantage of that is all that area is concentrated close to the axis of rotation. But an I section pushes all that area out to the ends, or pushes a lot of that area very far away from the axis of rotation. And because of that, basically I gets bigger the further out you can push that area from that axis, right? And if I push that area closer, so I just have like a rectangle right here, then I would drop. You get a lower moment of inertia. So in summary, moment of inertia, I, is a measure of how area is distributed in relation to that axis. And the further away that area can be pushed, the higher your stiffness or the higher your I value. So let me erase this circle here for a second. So we know this I-beam or I-column could rotate or buckle around this axis, but it could also buckle around the y-axis. So there's another axis that goes right down the center like this. And if it buckles around that axis, well, try to orient your head this way and look at how this area is in relation to that axis, right? Well, now the area is pushed right into that axis. So if the column bends in that direction, it has a much lower moment of inertia because more of that area is concentrated right along the axis. And if the column buckles around the x-axis, this other axis, more of that area is pushed away from that axis, which means it's less likely to buckle. So we really want a column to buckle around, in this case, the x-axis and not around the y-axis, the vertical axis, okay? So that's what I represents. And basically, again, if the area is pushed far from the central axis, you get a very big I, which means a very stiff column. And the last step before we solve this equation and use it on a real problem is to understand what K is. So remember, K is a constant that represents the way that the two ends of your column are connected to other supports. And so there's really four that we're going to look at for today. And if you look at this equation, remember K is on the bottom of the equation. And so the bigger K gets, the smaller P critical gets. In other words, the larger the number of K, the less force this column can withstand before it buckles. So we don't want a big K value. We actually want a small K value so that this column can withstand more force, okay? So the first connection condition that you could have is called a pinned connection. So a pin is, I want you to think of a hinge. So like a door hinge, right? A door rotates around a hinge. It's connected in sort of a pin connection. It allows free rotation. So it's not rigidly connected in place. And so imagine there's like a sort of a door hinge connection or two pin connections on each end of this column so that, you know, if I were to release one of them, it would be able to rotate around the other side. And if I release the bottom, it could rotate around the top. So they're not very rigid connections. They're just free to rotate if they're left alone. And so that has a K equals 1 value. So that would just be a 1 here, which would not really change much. And then over here, we have what's called a fixed free connection. And so a fixed connection is like taking this column and like really driving it deep into the earth so that it's very fixed in place. So it's not free to rotate there, unlike the pin connection, okay? The free side is exactly what it sounds like. There's no connection there. So it's almost like sticking a flagpole into the ground and you've got this end just able to be kind of pushed about. So it's free. That has a K value of 2, right? Which is not good. So 2 is going to go as a big number on the bottom, which means it can withstand less force. This column will buckle very easily. And then we have a fixed pin connection. So that's K equals 0.7. So that's much smaller of a K value, which is generally a good thing. That means it's fixed on the bottom and it's pinned on the top. So the way it's connected to the two supports fixed and pin connection. And then we have a fixed connection, which has the smallest K value, K equals 0.5. That's going to give you a very stiff column. So typically a fixed connection would be like a really good bolting or welding job. So this thing cannot move or rotate on either end of the support. K equals 0.5 is going to end up giving you a very large P critical. So this can withstand a lot more force before it buckles. So that's the K value. And now that we know all of our values in this equation, we can set up a practice problem and solve it. Okay, so now we have all the necessary background information to solve a real problem involving columns. So let's say that we have a system with two columns supporting a beam like so. And let's assume that this beam is being loaded with a force right in the middle. And let's call that force 60,000 pounds. So we have a 60,000 pound force right here acting down in the middle. And so my first question is, okay, if there's 60,000 pounds of force here, with how much force is each column holding the beam up with at the supports? And if you guessed 30,000, you'd be correct. So there has to be a reaction force of 30,000 pounds at each of these supports, holding this beam up to resist this 60,000 pound force that's pushing down. And so if these columns are each pushing up on the beam with 30,000 pounds of force, according to Newton's third law of motion, for every action there's an equal and opposite reaction, which means if they're pushing up on the beam is pushing down on those columns, also with 30,000 pounds of force. So let's just analyze one of those columns. And so here's what's going on with the column. The beam's pushing down on it with a load. I'm going to call that load P because that's going to match our column equation. And we just said that's 30,000 pounds of force. And let's give some more information. So let's say the length of these columns is 14 feet. So L equals 14 feet tall. And let's say that it's got an E, a modulus of elasticity value that was, remember, acquired from a laboratory test. And let's say that E value is 60,000 PSI. And so PSI stands for pounds per square inch. That means this material that makes up this column, probably steel because it's really high, could withstand 60,000 pounds per square inch of tension. You could pull on it with that much force per square inch before it starts to yield, okay, or fail. So that's a lot. This is a very high E value. It's a very, very stiff material. And let's say the moment of inertia, let's call it an I column. So let's just say it has this kind of cross-sectional shape. And let's say that based on the dimensions of that I shape, it has a moment of inertia, capital I, equal to 576 inches to the fourth power. So moment of inertia has a very strange looking unit, and I'm not really going to get into why it has units of inches to the fourth, but let's just say that that's the unit of moment of inertia. It's not going to be super important for solving this problem. And I think now we have all the info we need. Actually, one more piece is missing. We're going to say it's a fixed pin connection. So it's fixed at one end and pinned at the other, which means the K value is equal to 0.7. So for a fixed pin connection, I'll just write that here, fixed pinned. It has a K equals 0.7 for that kind of connection. So we have our E, we have our I, we have our K, we know the length of the column, and of course we know what pi is. And so now we're able to figure out what is the maximum force that this column could withstand, aka the critical buckling load. And we're going to compare that to this 30,000 pounds that it's actually feeling from this beam here. And if this 30,000 pounds is greater than that force, then the column will fail. But if this is less than that critical buckling load, then the column will not fail. And so we're checking for failure. So let's go ahead and find out if this column fails or if it does not. So we have our equation, and I'm just going to plug in all of my values. So we have pi squared on top times E, which is 60,000 PSI. So I'll write 60,000 PSI times I, which is 576 inches to the fourth. 576 inches to the fourth power times the, well, that's it. So that's the top. On the bottom, we have K which is 0.7, times L, the length of the column, which is 14 feet. But be careful here because everything else is in terms of pounds and inches, right? Pounds per square inch, inches. And if all of that stuff is in terms of inches, we can't leave this in terms of feet because that's an incompatible unit. So let's change that to inches. So how many inches are in a foot? There's 12 inches per foot. And so now we've converted feet into inches by multiplying these together. And remember that KL, that entire quantity KL on the bottom, so I'll put parentheses around all of it, is all squared together. And so once we enter all of that into the calculator, all together in one step, we'll be able to calculate that critical buckling load. So I'm going to go ahead and pull out my calculator now. And so on top we have pi squared, I'll do that, times E, that's 60,000. Remember, that's a measure of stiffness, times I, 576, also a measure of stiffness for this column, divided by KL squared. Remember, K is the condition of how it was connected at the top and bottom. So 0.7 times the length of the column, 14 feet, times 12 inches per foot, and then all of that quantity squared. I get 24,663. So 24,663.73 pounds. And so this, again, is called the critical buckling load, the Euler critical buckling load. And that is the maximum force this column could withstand before it buckles. And so it's 24,000 approximately. And it's feeling a force of 30,000, which means P actual is exceeding P critical, which means failure. This column will definitely buckle, right? And so that's the whole procedure. That's how we do column analysis. We basically figure out our setup and then we plug in the numbers and we check that the actual force should be less than the critical force. If it's too high, we know this column will buckle and we need to redesign. So how can we redesign this column so that it doesn't fail? Well, now the engineer would go back and say, well, I want bigger numbers on top so that this P critical increases, right? So it's more than 30,000, which means I need a bigger E, a bigger modulus of elasticity. That means I need a material that is more stiff. So if I'm using steel here, maybe I use a higher carbon steel that can give me a bigger E value, like 68,000 or 70,000. So we can test that and see if it's big enough. I also need a bigger I value. So remember, I means I can take that cross-sectional shape, and if it's an I-beam, I could try making a bigger I-beam, right? Bigger, taking those flanges and pushing them further out, because remember, the further out you push them, the bigger your I value gets. So this would be a more rigid column. I could also just make it beefier, right? So make that I beam much thicker. That's going to increase that I value as well. So I have some options there. Or I can look at these and adjust these, right? So what should I do with the length? Well, I should probably try to have a shorter column, less length, because if the L is shorter, I'm going to get a higher critical buckling load. So maybe that could withstand this force. But the architect or the building owner might say, hey, we need a 14-foot column, so you have no room to play around there. So you have to think of other places to change this. And that means maybe you're changing K, right? So maybe instead of a pin fixed connection, I use a fixed connection. That would give me a K of 0.5, which would give me a larger overall P critical, and that might be enough to get me over this 30,000 mark. So the engineer has a lot of options for redesigning this column, but I know as is, it's not going to work. We're going to experience buckling. Thank you for watching Fantastic Physics. Please like this video and subscribe to our channel if you want to see more interesting physics content. Goodbye for now, and remember, it's a fantastic universe out there, so stay curious.